That sounds wonderful. Thank you so much, Luis, for that kind introduction, for inviting me to speak. I'm very excited to be here today and to tell you a bit about the work that we've been doing on understanding past, current, and future human motion. So my name, as of very recent, is Lukas Rosenberger Schmid. Until 2 weeks ago, it was only Schmid. And I've also very recently moved to the University of Technology in Nuremberg, where I directed the Machine Intelligence Group before I was, as mentioned, at MIT. So now let's jump into it. As of today, maybe a bit as a motivating example, commercially successful robots mostly operate in environments like these over here. And while things are moving and dynamic, usually there's not that many people around and also not that much perception involved. But one vision I think that we all have is having robots as part of our everyday lives, of our homes, of social, assistive, and care facilities, public spaces. And one reason why I believe we don't see robots as parts of our everyday life as of now is because from a perception perspective, these kinds of environments are extremely challenging. There's very complex geometry, there's all the fine detail you need to understand, there's rich semantics, meaning all of the different things that the robot or a human might want to interact with. And then finally, and this is why we're here today, people are constantly moving around and imparting changes on the scene, which renders the scenes very dynamic and very hard to understand. So in order to address some of these challenges, our group works first on 4D perception, sort of building an understanding of what is moving now, what has moved in the past, building a dense reconstruction of where things are, or essentially reasoning about all of the sensor data that the robot has collected. Then based on these representations, we want to predict what are future trajectories, future changes, or unseen parts of the environment, which is very much the spirit of today's workshop, essentially reasoning about what the robot did not see. And then finally, because we want these representations to be useful to do interaction, we also want to use the robot embodiment to move through the environment, but importantly also to go and collect the data to build these representations that are most useful to complete the tasks. And then finally, and most importantly, we want to bring all of this together to essentially learn from what the robot has observed with a system that over time specializes to a specific environment, embodiment, task, or human preference. Today, I will be mostly talking about prediction, but also a bit about the 4D perception and scene understanding. I will start with maybe for the more junior researchers in the room, a brief overview of how I think about dynamics in the perception perspective. And we actually recently wrote a textbook chapter on the matter. So if you're curious, be invited to read it. It's going to be printed by Cambridge University Press, but the book is available for free as a digital version. So if you're interested, please give it a read. And sort of the main point that I want to make here is that how we think about dynamics from a robot perception perspective is essentially a matter of the observer. So very much like quantum physics, if you have the same physical trajectory, some human or object starts at some point, it has some trajectory through space and ends at a different point, there can be very different observations of this kinds of phenomenon. So first we have robot 1 who continuously observes the trajectory, and what we will see from the robot perception perspective is this like sequence of transient change characteristics, and I can track this through of the different views, and we typically call this short-term dynamics, these like transient change characteristics. Now imagine you have a second robot who sees the object, who then leaves the room, comes back and observes the final state again. What we then get are very abrupt change characteristics, which we call long-term dynamics. So this is usually more of a global problem. And to also emphasize the point that this is not necessarily a question of the dynamics of the actual object, I here have a couple of examples, because I think it's really about the rate of change, how fast are things moving, versus the rate of observation, how frequently are you observing what is moving. Where, again, the short-term dynamics is if we observe comparable to how quickly things are changing. Now, as an example, here we have a plant growing. For example, we take weekly measurements of how it grows over time. And while the underlying phenomenon is very, very slow, this takes months to grow, the kind of dynamics are actually very incremental from measurement to measurement. And also the methods used to solve these tracking problems are much more closer to, for example, human post-tracking, so tracking-based approaches. On the other hand, classical example of persistence monitoring, maybe you come back every day, scan the environment, you see that the furniture has been rearranged or changed. It's a very classical case of change detection, which would be long-term dynamics. But long-term dynamics doesn't have to be temporarily wrong, right? Here we see an example of an agent, in this case me, rearranging the scene within 30 seconds of the robot looking away. And it doesn't matter if the robot comes back in 30 seconds or a year later, it will sort of have the same observations. And as a final example, even things that move very fast with specialized equipments can be tracked very fast, where again we use tracking-like approaches. So in the past, we've done a lot of work on both short-term dynamic motion detection, where you see like classical reconstruction has all of these artifacts, like these trails behind, and artifacts that are not cleared from the map. But if we use essentially motion-aware reconstruction approaches, we're able to figure out which parts are moving and in turn also improve the reconstruction. So here again, local data association tracking is the name of the game. On the other hand, if we look at long-term dynamics and we want to reconstruct this in an online pipeline, which we for the first time investigated back in 2022, you get all sorts of different problems over here, such as new objects not being correctly captured, old objects not being completely removed, which we call semantic inconsistency, and different objects being merged together. And again, there you need specialized methods that are aware of these long-term dynamics to be able to reconstruct these human-centric changing scenes. So here we need to perform global data association and again talk about this semantic consistency. I want to present one work very briefly, which is on the long-term dynamic side, which is very recent and very exciting to me. To illustrate this point, is going to be presented at CVPR on the weekend, where here we see data capture from an area glass. And like during the capture process, people have interacted with the scene and some of the furniture has been rearranged. Now, the main challenge is if we want to train a high fidelity 3D Gaussian splatting reconstruction, we use all of these keyframes to train our models. And if you use state-of-the-art methods, we get all kinds of problems of this change in consistency. So here we see like the image is there twice, but also not really accurate. Lots of things are blurry, fuzzy, and not well captured. So in order to address this problem, we introduce a pipeline that is so far very standard. We start with the observations from the robot camera. We perform keyframe-based SLAM, so we only subselect a number of the methods or of the frames. And then in a sliding window, perform optimization to get this very crisp, high-fidelity 3D Gaussian splat representation. Now, to deal with all of those changes and challenges that I've mentioned, is we first need to figure out what are all of the changes since we've last optimized our model, where we need to essentially figure out objects that have been added while the robot was not looking, which is very different from allocating new Gaussians for unobserved parts, because you will already have a crisp rendering, but it will be conflicting with what the robot observes. And of course, we have the same problem for things that are removed, which you also need to remove in order not to jeopardize reconstruction. And the other bit that is particularly hard for 3D Gaussian splatting is because we use all of those keyframes to optimize our representation. We also need to go back, find the covisible keyframes, and mask out all conflicting bits. So I'll give you an example here of an object appearing. We have the input image as observed by the robot camera, and we see the rendering of the current incrementally reconstructed scene back to the robot camera. And we see this conflict here shown in red. So we can use depth comparison, color comparison, semantic comparisons to figure out this coffee machine has newly appeared. Now we need to go back to all of the previous keyframes and essentially say these are areas which will be occluded by the coffee machine in the future, so don't use these for optimization or the coffee machine will get fuzzy. Things become even harder if we look at the disappeared case, where we here see again a conflict detected, the bed has disappeared. But if we now go and render back the conflicting parts, we have occlusion, all sorts of things. We see maybe over here, only half of the bed is reconstructed or is detected as missing. And this is really where we see geometry fail, because you get like half beds floating around, which we as people know is not very likely to happen. Therefore, we also need to have this sort of completion of semantic consistency, where we need image-based models to tell us these are things that move as a unit, move as a whole, no half beds floating around. And if you integrate all of this into the pipeline, we actually get very exciting results. You see on the bottom right our method. We see on the left two state-of-the-art methods that are designed to reconstruct static scenes, and on the top a state-of-the-art method to reconstruct short-term dynamic scenes, so people moving in front of the camera. And we see that all of these methods don't do particularly well in our case, whereas our method is able to get a crisp reconstruction of all of the things that have been changed by people while the robot was not looking. And because we have these high-fidelity Gaussian splats, we can also detect geometrically insignificant changes, like the painting that had been changed on the wall. Now, after I've been belaboring you a bit about short-term dynamics and long-term dynamics, ideally we want to have a system that can both deal with people currently moving in front of the robot, as well as changes imparted on the scene by agents while the robot is not looking. And usually these two problems are addressed by separate communities and separate works, so we thought ourselves, can we actually bring this together in a unifying formulation? And we very verbosely coined this problem the spatiotemporal metric semantic SLAM problem, which is exactly a description of what we're trying to do. So on the one hand side, we want to build a 4D representation, meaning what was the scene like at all times and not only a best running estimate of what we think the scene is like now. And of course, we want this to be spatially, temporally, and semantically consistent. We also want to have a dense reconstruction and object level understanding of what is going on here, such that representation is useful for interaction, navigation, planning, and reasoning. And then finally, we want to do all of this in a simultaneous localization and mapping fashion, meaning we also estimate globally consistent robot poses and run all of this incrementally on board compute-constrained mobile systems. And we can actually formalize this as a probabilistic maximum a posteriori estimation problem, where at each time step, capital T, we try to find the set of all objects in the background, denoted O star, where each object, OI, consists of a surface, omega, which can be time varying, so it can be deforming. It has a pose T, which can be time varying, so it can be moving. And it has a semantic label or feature, which for now we assume is constant. At the same time, we want to find the robot poses based on measurements of the environment and of the robot's ego motion. And what we find is, unsurprisingly, that this is an extremely challenging problem to optimize. There's a very large number of variables, since everything can change over time. The problem grows very quickly. And importantly, there's a very strong coupling between the different variables and different sources of errors. So for example, if the robot makes a measurement that disagrees with what our belief over the scene currently is, there's many potential reasons for this. Maybe we're in the right place, but the scene has changed. Or maybe the scene is the same, but the robot doesn't really know where it is. Or it's actually in the right place, but the measurement is just very noisy. So this is very hard to disentangle. So what we show in the paper is that by making very lightweight assumptions of local consistency, meaning the odometry is of a drifting nature, the error can grow arbitrarily large over time, but it doesn't jump around. And we do the same for the physical change. Change can be arbitrarily large over time, but people don't teleport around. We can find a factorization of this problem that looks more complicated, but it's actually much more easy to solve. So if you first have this local estimation problem, where we try to find locally consistent fragments of observations, here called the Ys. This is the only thing that depends on the measurements. So essentially the idea is, as long as you observe something moving or being there, you can be pretty certain that it hasn't been changed or moved otherwise. We can then optimize over the spatial layout of these fragments and finally put everything together into a singular 4D representation, which is much more approachable to solve and will give a good solution to this very hard initial problem. Now, we also designed a system based on exactly this factorization that we called Chronos, and this is what it looks like on a robot. So we here see it operating on this Jacko wheeled robot equipped with an Intel RealCells RGBD camera. It's a very noisy camera, so the reconstruction will not be a crisp Gaussian splatting reconstruction. But essentially, to really bring home this 4D nature of the approach, we here have a variable on the z-axis, which is the number of objects believed to be present in the scene, over two different time axes. So on one hand side, we have the wall time, capital T, elapsed for the robot, but we also have the belief over all previous times, lowercase t, for each real-time part. So naturally, the real-time axis is on the diagonal, meaning it's the belief about the current wall time. And what we find is that as the robot explores, more and more objects are being detected. Soon it will also see a dynamic object and deformable object which is moving around, which will be tracked for every frame and reconstructed. And then when the robot gets back to its starting pose, it realizes this is the same place. We will see the map being globally optimized, snapping back into position. This is where it happened. But now the robot also realizes that this chair over here that was previously there has disappeared, so the number of objects present decreases. And on the flip side, this cooler on the table has appeared, so the number of objects present increases again. Now, what is really exciting about this is, for example, you can ask questions like, given all of the data up until capital T equals 150 seconds, what was the world like at previous times? So you can play back this 4D history of where was the robot, where were the agents. and what was the environment like. And what is most important to notice here is our belief of when those objects appeared or disappeared has changed based on when we last saw them to be present and first detected them to be absent. So not seeing an object is very different from actively noticing that it's gone. On the other hand, if we just want to know what was the world like at t equals 20 seconds, we can have the robot gather more data in the future, and we see how the environment becomes more complete. The map is becoming optimized, this change detection performance is becoming optimized. We essentially have this flow of information back through time. And in this fashion, we, for the first time, were able to essentially build this optimization over 40 beliefs incrementally on board a mobile robot, which we presented at RSS 2 years ago. It was very exciting. Now that we have these dense reconstructions, so Kronos can give us the reconstruction of the environment, but also all of these different agents, like the moving people in purple, the persistent and changing objects in color. We also want to find higher level abstractions of meaning in this environment. And in our group, or Luca Carlone's group at MIT, we've been doing a lot of work in figuring out what are abstractions of spatial concepts, such as what is the topology of the navigable or free space, which you can represent, for example, in this places layer. You can further abstract this into individual rooms, into individual buildings, and so on and so forth. So like this hierarchical abstraction makes planning over large-scale domains very efficient because you can reason at the right level of abstractions. So what we're currently trying to do is, can we actually generalize this to temporal abstractions, such as which areas are most likely to be dynamic, what are predominant motion patterns, and so on and so forth. Now, the final bit I want to present on the perception side is if we want to have these representations as robot memory, so essentially want to ask the robot questions about what it's seen. What current methods do, there's a lot of excitement around vision language models, is you take a lot of these images, you put them maybe in a vectorized database, and then you get an agent that can query this database, query a VLM to give you answers. But what these methods inherently lack is this sense of spatial consistency. So here we see, for example, observations of a couple bicycles, and more observation of the bicycles, and more. And what the agent will tell you, there is heaps of bicycles over here, it's crazy. But it doesn't get this concept of it's actually the same few bicycles seen from different views. So we thought to ourselves, people in the mapping community have been solving these problems for years, right? Ideally, we would get this representation that is consistent of the environment, but still having highly detailed semantic descriptions of all of these things that can then be queried by a vision language model to answer these questions. So we also designed a pipeline that is also going to be presented at CVPR on the weekend, where we start from the input sensor data. We then feed them through a front end like Kronos's, where we get all of these segments of objects or agents from the environment purely from geometry. And this is really efficient. This runs in real time on a CPU. Now, the big question is, if you want to build an expressive memory, right, you want to take your big and beautiful frontier model, the biggest thing that is out there that gives you the best performance to describe these representations. But at the same time, we do want to run these things on our mobile robot with limited hardware. So what I essentially decided to do here is come up with a pipeline to select only specific images that we then send to the vision language model, where the key idea is we can frame this as a two-stage optimization problem. So essentially first, finding the minimum number of pictures that we need to send to the VLM to capture all of these fragments, in a sense, the set covering problem. But we also subject to maximizing a view quality heuristic. So here, for example, lots of partial observations, not likely to give you very good descriptions from a vision language model. 3 is looking pretty good, but we would need to query more images to also get information about the human. So in this case, we would choose to only send picture to the VLM to get good descriptions of all of these tracks that we have. We can further optimize this by using set of marks prompting. So we prompt all of these things at the same time, which actually gives very good performance in reasoning models, and also implement this as batch inference to reuse as much computation as possible. And with this kind of architecture, we get this semantic lifting of comparably expensive models like describe anything in a real-time pipeline. And by real-time, I of course mean we process all of the frames and have the geometric safety and tracking at around 10 Hertz, I think. But of course, running these models is expensive, so we get latency of around 10 seconds, but we think this is a fair trade-off if you're interested in building a long-term memory that you can later query. we can actually apply the same logic to the background and extract these places or navigable spheres hierarchy. Importantly, we do this global optimization and data association to figure out which are the things that should be belonging together. And we end up with these 40 scene graph of highly detailed descriptions of all of the different levels of abstraction. And what is very exciting about it is here we can see it run. The robot collects all of this data. We can see how the background is incrementally reconstructed, while with some latency also the semantic lifting is happening. And we ran this on fairly large data sets up to 35 minutes and 1.5 kilometers of scale, and are able to extract these scene graphs quite reliably. Now, once we have the scene graph, we can ask all sorts of queries like spatial queries. Where did you see the sculpture in front of the computer science building? And we actually use an agentic retrieval system where we also equip it with tools to query specific things in our hierarchical scene graph. So for example, it first uses semantic search where we get different things that are similar in language description to sculpture. Then it thinks, let me check for the different regions. Let me get the high-level descriptions of where different things are. And after it then goes and verifies the few things that it's found. That's actually very cool to see as an action by the model. And because we still have this underlying metric for the representation, we can actually get very accurate answers in our metric space of where the things are that we want. Similar logic for temporal questions like when did you walk by the crosswalk in front of the Texas entrance? We again have the agent query different things, and we don't tell it what to do. It first chooses to use a semantic search for descriptions of the crosswalk entrance, then queries information about the trajectory of the robot that is also stored in the scene graph, and then gives a very detailed answer on how much time has elapsed from this 40 scene graph. And what we found very exciting to see is comparing against state-of-the-art methods with fairly expensive vision language models, as well as mapping-based methods in concept graphs, also with the most recent versions of ChatGPT. For a range of different questions, we're able to get massively improved performance by essentially having this hierarchical, consistent structure, spatially consistent structure that you can build incrementally. Now that you sort of have like these models of what the robot has seen to be currently moving and to have changed in the past, I finally come to the bit that you're probably most excited about, is how can we use this to predict the futures that are going to happen. So here I very briefly want to mention one work. We start with the easier bit of how do we do long-term change prediction, sort of figuring out what is going to change in the environment. And we first had to define what are things that can change, right? There can be semantic state changes. This armoire can go from a closed to an open state. There can be position changes, objects are being moved around, as well as instance changes, objects being added or removed from the environment. And what is really cool is from observations of the scene, you can go to these hierarchical abstractions in form of a semantic 3D scene graph. And based on only local relations between different objects, agents, and places, you can train a graph neural network to predict you what is the probability of these things changing in this high-level symbolic semantic space. But we also get the return ticket to the physical world where we know these are the objects that are most likely to have been changed. Now, what we learned from this is scene change prediction is a really, really challenging task because it's a highly, highly multimodal prediction problem. The main intuition here is there's a plethora of possible futures that are possible or even plausible, but only one thing will happen. So if anyone ever reports very high accuracy on this task, I would be a bit afraid that they overfit to the test set. However, what we found is we learn really good general priors about which things people are likely to interact with based on these change observations. So for example, monitors most likely to change their state, frequently interact with object. We see that like frequently interactive things like chairs are most likely to be moved around, and especially find like a chair behind a desk is more likely to be moved around than the chair in the back of a conference room, which is maybe a bit more static. And of course, like small and handheld items turned out to be the most likely to be added or removed from the environment. Now, while the overall prediction performance was poor, we got around 70% accuracy, I was really excited to see that it is useful for downstream robotic tasks. So here we see the distance traveled in an active change detection task. The robot goes around and figures out what has changed in the scene. And we find that compared to an optimal coverage path computed in orange. Using this learned prior from observations, we're able to complete the task 66% faster on average. So even like a not very accurate, but better than random prior can be useful for downstream tasks. Now, the final work that I want to introduce today is how do we generalize this to motion prediction of people and not just their interactions, where usually we have a person, we have some observation of what has happened in the past, their trajectory, maybe some interactions, and we want to predict the future. And there is a large body of work who looks at futures of around 4.8 seconds, which is amazing to do collision avoidance or navigation. But if you want to do, for example, proactive interception or avoidance, and you want to scale this to much longer horizons, usually what you see is trajectories become extremely nonlinear and hard to predict. So here the key idea, again, is if we had all of this knowledge about the environment, for example, which objects, agents, and rooms are there, would this information help us to predict where the person is likely to go? So we again have this idea, we start with the physical scene, we perform this hierarchical abstraction into the 3D scene graph, and here we assume the robot has already mapped the environment, and now we want to do the motion prediction. And what we find is these high-level symbols interface extremely well with, for example, large language models, where we can do interaction sequence prediction. So what are sequences of things this person might want to be doing, given our knowledge of the scene and of its past actions? And as mentioned before, it's really important to get this return ticket back to a spatial grounding because we're interested in trajectories, but also the temporal grounding because a trajectory is something that evolves over time. And as mentioned, very multimodal problem. So ideally, we want this 4D probability distribution over future human positions, from which we can also sample candidate trajectories. I'll very briefly tell you how this works. We start with a bunch of observations where the robot is right now. For example, they shut down the PC, stood up from the chair, and we can use the LLM to predict things that are likely to happen. For example, they want to pick up the coat or go to the coffee machine, and we can really make a tree of a hypothesis of what a person might want to be doing. And based on these interactions, we can then use the spatial grounding we have in our traversability in the places layer to figure out what would be efficient trajectories to complete these high-level objectives. And for the final bit, the temporal grounding, we thought it would be much easier to just look at transition probabilities, for example, different velocities the person might be traveling, different times it might be interacting with a coffee machine, for example, right? Ideal extraction time is around 30 seconds, and different probabilities of branching in this multi-hypothesis tree. And what is nice with these probabilities that you can either estimate or in our case just also get from the LLM, you get a very principled model in a continuous time Markov chain model. We essentially start the solution to this is known. It's actually very efficient to compute because it's a tree. And essentially start with all of the probability mass at the origin and then have this flow of probability mass through our spatially grounded tree, which gives us then essentially a probability for each time step. And this is what it looks like if we run it. We really see the multimodal nature. There's different things the person might want to be doing. There's different objects or rooms where the person is most likely to stay for longer times. And because it's a probabilistic model, we get all sorts of nice theoretical insights. For example, when is the prediction no longer informative and it never gets as bad as uniform, which was also an interesting insight. On the practical side, if we here look at time horizons on the x-axis into the future and the negative log likelihood on the y-axis, so the lower the number, the more probable is the true trajectory under your prediction, we see that not only are we able to scale to longer time horizons, but we also get a significant performance boost. So I hope I could show today that it's important to know what is happening right now, but also to have this understanding of the past, to learn from all of these observations, past trajectories, past changes, and of course then specialize to predict the future, to be proactive and interact with people efficiently. I want to very briefly announce two things before I finish here. I think I'm at time. We've recently released the 3D scene graphs repository. If you're interested in 3D scene graphs, we've categorized all papers that we could find on the matter on this online website. You can have all sorts of different queries. If you want to know, for example, what has been happening in hierarchical scene graphs by a specific author, you can get those papers. Or you can graph connections between different papers. So here we're looking at number of publications on scene graphs by venue. And we actually see that ICRA is the strongest. So keep up the great work in the robotics community. And we will release a survey paper on the matter in the coming 2 weeks, so stay tuned for that. Second final advertisement, while I've talked a lot about algorithms, we run a lot of these things on board of mobile robots. Everything I've mentioned today is available as open source code. It's been used by quite a number of groups in the community. Last time I checked, I think this is around a year old. If anything of this sounded interesting to you, please feel free to give this a try. Let us know what works. Most importantly, let us know what doesn't work and improve on it and write a nice paper. I'll be very happy to take questions now. If you have questions later, please feel free to shoot me an email. And as a final sneaky advertisement, I will also be hiring PhD students. So if it sounds interesting to you, please get in touch. Thank you so much for your attention.
Thank you, Lukas. Amazing talk. Really interesting, very comprehensive. We're just talking about that. Open for questions. If you have any questions, you can just raise your hand, or if you prefer to come here. All right. Yeah. Ahim. Oh, Ahim. Makes a bit easier.
Yeah, I can just repeat the excellent presentation. I was just wondering, sometimes you have this periodic changes, like doors open or closed, or the picture that is sometimes here or there. And I mean, from all you presented, it should be possible to say, okay, I have some old frames, keyframes. Are you using that already? I have some old keyframes where the chair has been already here, and I can use that.
Wonderful question and very acute observation. That is absolutely right. So we do try to use that information. For example, in Kronos, we keep essentially a timeline of all of the detections of an object being present or absent, and then use this to estimate, for example, when it most likely appeared or disappeared. That being said, it's very early stage work. There is much more to be done, especially also in like learning from these observations and specializing to the scene. That would be very exciting.
Please. Do we have time for one more question? Currently, I think you're using tools to enable your LLM agent to reason about these scene graphs. Is that right?
That is partially right. Yes. Let's finish your question first.
So my question is, do you think we need these tools in the future, and how could we encode these scene graphs, especially these massive scene graphs like in DAM, so that the agents are able to reason without tools?
That is a wonderful question. Thank you so much for pointing this out. We've actually tried a range of different things on how we can feed scene graphs to LLMs. And one thing that is nice, because it's already like this hierarchical symbolic abstraction, you can actually pipe the entire thing into a JSON file, give it to ChatGPT, and go give you reasonable answers. But what we also found, there's much smarter things that you can be doing. For example, Aaron Ray, a colleague of mine at MIT, has been doing cool work as like organizing the scene graph as a standard database. Whereas LLMs are actually very good at writing database code, or in DAM, we provide specific tools like querying semantic features, trajectories, regions, and so on and so forth, which turned out to work much better. So essentially, if you make the LLM's life easy, it will also give you better replies.
Thank you.
Thank you so much.